Hello, this is part 7 of the Impulse and Momentum video series. Today, first I'm going to talk about a completely inelastic collision, and then center of mass, and then a couple of examples, and hopefully finish this series with this video. So, completely inelastic collision, by definition, these do not conserve kinetic energy. Also, two objects stick together, they tangle and become one object, and they share the same after velocity. So object A with mass ma, its momentum is, before the collision, ma_va1. You add to this the momentum of the second object before the collision, mb_vb1. And after the collision, they stick together, so I just add the masses like this, times a common velocity, v. After the velocity, let's call it VAB. They share this velocity after the collision. So it's a really simple relationship. Usually these problems are asked with some additional energy conservation. So the first example is called the ballistic pendulum. Very standard. I'm going to show you a variation of it after this. So let's say you have a gun here, and it fires a bullet with the mass mb. So, and let this be the velocity of the bullet right before it hits a target. The target is capital M, and it's suspended from the ceiling with a cable like this. All right. So the bullet will embed itself in the target, and both will swing to a maximum angle of theta max. Okay, so the bullet is inside. Just like this, the total mass is now m plus mb. And the final speed here is 0. That's what I mean by theta maximum. All right, so think about it. This was the original direction of the bullet, or let's say a point you pick on the target, but now that point is above the original line. Let's call this H above. All right, so what happens is when the bullet is inside the target, because of momentum conservation, we'll have some kinetic energy. The system, which is the bullet and the target, will have a speed right after the collision, okay? So that kinetic energy is the all energy the system has. When it swings, the kinetic energy will become less, and the potential energy will increase. We could take this level as our reference for potential energy, and at the highest point, you have the highest potential energy, gravitational potential energy, while the kinetic energy is just 0 because the final speed is 0. Okay, so this problem requires the application of energy conservation laws. But a common mistake would be applying that conservation from the beginning all the way to the end. We can't do that. We have to divide this into two phases. Right in between the two, we have to actually think about the intermediary step here when the target has the bullet inside. Here's the bullet. The mass is m plus mb, but it hasn't moved yet, or it's about to swing. So at that instant, right after the target takes the bullet inside, it's got to have a velocity. That's why we have initially kinetic energy. So let's call this V, capital V. All right, therefore you will have kinetic energy equal to 1/2 mb plus m times v squared at that instant. Okay, but it's still at the horizontal, this reference line here. It hasn't started swinging yet. So there will be two phases for this problem. Number one, which is right here, where we need to apply momentum conservation. Momentum conservation. And then the second phase, once the bullet is inside, there's just one system. It's the bullet plus target. And we can conserve energy now. The mechanical energy will be conserved. All right. So the first phase tells us that the momentum before the collision, total momentum before the collision, will be equal to the total momentum after the collision. Initially, the contribution to the total momentum comes only from the bullet. So mb times vb. It's a one-dimensional collision, so it is the x component, right? And the target is stationary, so this will be equal to total mass after the collision, right after the collision, times this common speed, right? That's the momentum conservation. And from the energy conservation, which is phase 2, okay, now we have the kinetic energy, mb plus m v squared. And there's no gravitational potential energy yet, if you take this to be your reference. This will be your total mechanical energy, the kinetic energy itself. That will be conserved. So when the system is up here, it stops for an instant, so there's no kinetic energy, but we do have potential energy. So mb, not mg, mb plus m, the target mass, times g, acceleration due to gravity, times h, your h above the reference line. All right, so these are equations, and h could be found, h could be given, or if you're given the angle and maybe this length here, let's call it L, okay, then h will be L minus this part, which is the adjacent side to theta, L cosine theta m. So we know h one way or another, and suppose you can measure the masses, and therefore you want to find out what the original speed was of the bullet in terms of the masses and the height. Okay, so we don't need to know this v, so let's eliminate that. First, we can get rid of the masses here, it cancels. So V will be equal to square root 2 GH. The solution of this equation for this V. And then plug it in this and solve for VB. So here you have MB plus M divided by MB times square root 2GH. All right. A variation to this problem, similar. It's not a pendulum. Let's use an arrow this time. This arrow is going to fly into the target. The target is leaning against a spring. Okay, the mass of the arrow is M, target is MT. Now once the arrow is inside the target, it's going to deliver this momentum, and then the spring will be compressed against the wall here. Okay, let's say the original length of the spring was L0. But now it is L. So there's this much compression there. Okay, same idea. First, conserve momentum. This is V. So M times V will be equal to M plus M target. A new velocity, call it V prime, right there. And the kinetic energy, 1/2 M plus M target V prime squared. Now this will be used to compress the spring. So you're gonna store energy in the spring, and that is given by 1/2 K. The compression is L minus L naught. So you take the square of that. So this will be the energy, where K is the spring constant. K is the spring constant. So let's get rid of 1/2 here. And V prime will be equal to K divided by total mass times L minus L naught squared. Therefore, the speed of the arrow right before it hit the target, M plus MT over M times K divided by M plus MT times L minus L naught squared, or 1 over M times K times M plus MT L naught squared. Okay, let me stop here. In the next video, I'm going to go over the concept of center of mass.